Chapter 11. This is a quote from Thomas Kuhn. No theory ever solves all the puzzles with which it is confronted at a given time, nor are the solutions already achieved often perfect. We're going to be looking at two more bonding models, the valence bond theory and the molecular orbital theory. And we're also going to look at a theory that uses Lewis theory to describe molecular shapes. And all of these are very helpful and useful, but they are only models, and they have their limitations. So, VSEPR theory, VSEPR, that stands for valence shell electron pair repulsion theory. And this is based on the idea that groups of electrons repel each other. It's a very simple model for predicting molecular shapes. And we're looking at electron groups. I know the name says electron pair, but we're looking at electron groups. So this is an important thing to remember. What is an electron group? A lone pair, single bond, a double bond, a triple bond, or if you have a free radical, a single electron. We're not going to see any single electrons on the things that we're predicting shapes of. And this is why on worksheet 10, I asked you to identify how many lone pairs and how many electron groups were on the central atom, because that'll give you a head start. So here's the idea. We have this central atom, and here's a pair of electrons acting as a bond between these two atoms, and there's another pair of electrons and another pair of electrons. Now, it is a bit mysterious how the two electrons in the bond can exist with each other, but they can coexist in an orbital, so they must be able to do it here. I think it has to do with their spins. But this group is going to repel the other groups. And so they're going to try to get away from each other. They are attached to the central atom, but they can move around the central atom. So I think of these as a little bit like being a person on the earth, right? So you're a person on the earth, and there's two other people that you really hate, and they hate you equally, right? And so you're going to get as far away as possible from each other, right? So you're spread out around the globe, right? In opposite directions. And for three things, the biggest separation you can get is if there's a 120-degree angle between you. So what we're looking at is repulsions between electron groups on interior atoms, and that's going to determine the electron geometry. Preferred geometry has a maximum separation of groups. So let's look at beryllium chloride. I'm going to draw these. This theory is based on Lewis structures, so we're always looking at the Lewis structure first. So for beryllium chloride, we're going to have beryllium and two chlorines, and then beryllium has two valence electrons, and then chlorine has 7, so 14 and 2 is 16. 2, 4, 6, 8, 10, 12, 14, 16. Now, I didn't give an octet to beryllium, but remember that beryllium and boron will sometimes be satisfied with an incomplete octet. They are too small to make multiple, to expand octets, and so, they just sometimes settle for less. So if we look at our Lewis structure, then we need to identify how many groups are there. A single bond is one group. So this is one group here, and this other single bond is one group. So we have two groups. So here, the beryllium atom is the Earth, and this is you, and this is your ex, the worst person ever, right? And so how do you get as far away from them as possible? You go on the other side of the world, right? You can't get any further. So these are on opposite sides of the central atom. It gives them as much space as possible. That makes sense? And if we look at the bond angle, this is 180 degrees. So bond angle is a useful way of measuring the separation. So this geometry where the three atoms are in a line is called linear. Okay? Let's look at carbon dioxide. Now the point of all of this is not to review drawing Lewis structures. So I'm just going to try to draw these quickly so that we can get through all of the stuff we need to get through. So there's the Lewis structure for carbon dioxide. How many electron groups on the carbon? 2. A double bond is one group because these two bonds cannot move away from each other. They are both stuck between the carbon and the oxygen. And this double bond is another group. So 2 groups. They'll be on opposite sides and we'll see a linear geometry again. And we can look at balloons. That's why I have all these balloons over here. And this is something you can do at home if you feel like it. Turns out that tying them together is harder than it appears. I've been practicing for a while, so hopefully it'll go well tonight. So what I'm doing is I've got a piece of string, essentially, tied to each balloon. And there I've got 2 balloons tied together. And so they both, take up space, and so I've tied them together at the narrow end, and so they're going to be across from each other. So that's the equivalent of a linear geometry. So what happens when we put a third balloon in there? So I'm going to add this third balloon. Come on, string. There we go. So when I put the third balloon in there, it pushes the original 2 balloons a little bit closer together to make space for the third one, right? I don't want to pop those on my keys. So that's what we've got going on here. This is a ball and stick model of boron trifluoride. I forgot to draw the Lewis structure. And again, boron will sometimes have an incomplete octet. And that's what it's doing here. So we look at the Lewis structure and we look at the central atom and ask ourselves how many electron groups? Well, there's 3 single bonds, each is a group. So this is 3 groups. So this is like 3 balloons tied together. We've got 3 things trying to spread out and get as much space. And so the best they can do is get 120 degrees. So this is called a trigonal planar geometry because if you look at the overall shape, it's a triangle, right? It's a triangle and it's in a plane. So if you look at these balloons and imagine a plane going through the middle of all of them, right? They are all fitting on a plane, not an airplane. So that's the trigonal planar geometry. Formaldehyde also has 3 groups. Here's the Lewis structure. Here the groups are a double bond and 2 single bonds, still 3 groups. And so those 3 groups will try to get away from each other. They will take on a trigonal planar geometry, But now the bond angles are not equal as they were for boron trifluoride, because the oxygen with its double bond is more repulsive than the hydrogens with their single bonds. And so this hydrogen and this hydrogen hate each other, but they hate oxygen more, right? So they're going to have a little more space from oxygen, and they're willing to get a little bit closer to the hydrogen. Any questions yet? So here's a question. A central atom in a 3-atom molecule forms 2 double bonds and has no lone pairs. What is the geometry of the molecule? I heard linear. That's correct. So this is one you kind of have to draw unless you're good at visualizing things. So you've got a 3-atom molecule. So I've got 3 atoms and 2 double bonds. So double bond between those 2, double bond between those 2. So there are 2 electron groups. 2 electron groups makes a linear geometry. When we get to 4 groups, now this is no longer planar, it goes into 3 dimensions, and so it's a little bit trickier to look at, and that's where the balloons come in, is super handy. So I added 1 white balloon to the blue balloons, and it's a little hard to see, but the white balloon is kind of pushing the blue balloons down a little bit, right? So here's the balloon analogy slide. So the linear geometry is like 2 balloons tied together. Trigonal planar, 3 balloons tied together. And here, the balloons are representing electron groups, not atoms. Those are the electron groups. So the 4th balloon, when you add it to the trigonal planar, it's going to take up space, and it's going to force these balloons slightly out of a plane. So these guys are kind of at an angle now. And this shape has a name. It's called a tetrahedron. It has 4 sides, but it's 3-dimensional, unlike a cube, which has 6 sides. It's made up of squares. Tetrahedron is 4 triangles. And the angles here are 109.5. So here's another way to draw a tetrahedron. So this would be the end of 1 electron group, the end of another electron group, 2, 3, and 4. Any questions? So methane has 4 electron groups. Here's its Lewis structure, 4 single bonds. So when we look at the Lewis structure, it looks flat, doesn't it? Because we drew it on a screen. It is flat. And the angles here between the hydrogens look like they're 90 degrees. Well, they are 90 degrees in a flat 2-dimensional situation. But molecules don't exist in 2 dimensions, they exist in 3 dimensions. So when you get that 4th group in there, now we have to consider 3 dimensions. And so they will make this tetrahedral geometry with bond angles of 109.5, because that's more separation than 90 degrees. So let's look at this, the HCN molecule. We've got the Lewis structure given here. How many groups, electron groups on the central atom? 2. So what's the geometry? Linear. You can draw it different ways. Now you could draw it like this. But that doesn't make it look like that. right? We're looking at the number of electron groups. So if we put in a fifth electron group, come on guys, you can get together. So now it makes this shape. So this is called a trigonal bipyramid. So we have, oops, just killed it. We have a trigonal pyramid on the top, that's this part, and a trigonal pyramid on the bottom, that's this part down here. So it's two trigonal or triangular pyramids, as opposed to a square pyramid that has a square at the bottom. So it's a trigonal pyramid, it has a triangle at the bottom. And there's two of them stuck together, so that's where the bi comes in. Trigonal bipyramidal. And the good news is, I'm not going to check your pronunciation or your spelling on an exam. You just have to be able to choose the correct words. So that might make you feel a little better. So this is a picture of the balloons, right? I've got the balloons over here. This structure is a little bit strange because the bond angles are not all equal. If we look at this ball and stick model, there's one group that's going straight up and one going straight down, and then this one's coming out in the middle. And so these bond angles are 90 degrees. But if we look down at it from the top, we see a triangle, and the angles between these guys are 120 degrees. So with these balloons, what I did is I made the white balloons going up and down, and then if you look at the end of it, you see the blue balloons are making a triangle. Okay. So we have names for those different positions. The up and down ones are called the axial groups. They are on the axis, and so this is like the Earth, right? It has an axis that goes through North and South Pole. And then these guys are along the equator, right? The equator circles the Earth right in the middle. So these are equatorial, and that one's axial. Any questions? If we stick another group in here, now we've got 6. These are getting a little crowded in balloon land. If you try to do this at home, it helps if your string is not slippery. So I'm using cotton yarn. Okay, there we go. So there's the picture of the balloons. This shape is called an octahedron. There are 8 sides. A tetrahedron has 4 sides, octahedron has 8 sides. So there's 1, 2, 3, 4 on the top, and 1, 2, 3, 4 on the bottom. This could also be called square bipyramidal, but they don't call it that, which is nice because octahedron is a little more familiar. So we could still look at this in terms of axial and equatorial, but in the octahedron, all the bond angles are the same. They're all 90 degrees. So in my head, I imagine this as being like a little girl or a little boy. And this is the tutu, right? They're in ballet class. And that's the tutu, and they spin around. So in my balloon here, the white balloons are the little person, and the blue balloons are the tutu that sticks out as they twirl around. Okay? So we should be able to do things like this. Determine the molecular geometry of CCl4, as carbon tetrachloride. The first thing is draw the Lewis structure. So if you need some help with your Lewis structures, let's be sure to talk about that during lab tonight, because Lewis structures are on the exam on Wednesday. This shape stuff is not. So CCl4, we'll put the carbon in the middle. We will put the carbon in the middle, not the chlorine, good grief. And we'll attach the chlorines to it, and we'll spread them around. Lewis theory is two-dimensional. Everything's flat. And then we would count up the number of electrons, the valence electrons, 4 from carbon, and then we have 4 times 7 for the chlorine. So, 32? Yeah. And then I have to consider the bonds I've already made, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. These lone pairs don't show up in anything we're talking about with VSEPR theory. But if you don't put the lone pairs in there, you might miss that you need a double bond or something, where you might have lone pairs on the central atom, and those matter. So how many electron groups on the carbon? 4. What shape do 4 balloons make? Tetrahedron. Oops. Keep using the fat marker. So tetra is a prefix that means 4, right? And I'm pretty sure that hedron means shape, like octahedron, tetrahedron. Any questions?